In Chapter 2, we got down the basics of atoms. We learned what atoms are, and we went through the experiments that taught us the different parts of the atom. Thomson taught us that electrons exist and hypothesized that there had to be a positive component to balance out the corpuscular electrons, though he was wrong about what positive charge looked like. Millikan's oil drop experiment helped us define what electrons were by finding their absolute charge and mass. Finally, Rutherford's experiment showed us that Thomson's hypothesis about positive charge was wrong. Instead of being distributed throughout the atom, it was concentrated in the center in a region called the nucleus. Although we didn't talk about it in class explicitly, James Chadwick followed up and rounded out our understanding of subatomic particles when he discovered the existence and mass and charge of the neutron. So that opens the question of, where are the electrons? And they don't really have much mass, which is weird. So what exactly are they then? These are the questions that we'll devote some time to over the next few lectures, specifically in Chapter 3. We know that even though they're small compared to protons and neutrons, electrons still are particles that have a mass. However, in addition to being particles with a mass, electrons also exhibit wave properties. Specifically, when electrons collide with other molecules, they can release a particular frequency of light that corresponds to the amount of energy released or absorbed. But before we get to that, let's back up and review some of the properties of light, or if we're thinking in bigger terms, electromagnetic radiation, or EMR, as I like to abbreviate it. Electromagnetic radiation is a term for the energy released in wave form when charged particle collides with another particle or accelerates in space. Or, as the book likes to define it, radiant wave-like energy and the electromagnetic spectrum. There is a broad spectrum of these types of waves and energy, which vary in the energy they carry, of which one small part is the visible spectrum that we associate with light and the different colors. For simplicity's sake, we are only going to think about the visible spectrum to start. So let's start with a basic light wave here. We can start by classifying two properties, the wavelength being the distance, typically in nanometers for the visible spectrum, between two crests or troughs, and the frequency, which is the number of cycles that are completed per unit time. We typically use the unit hertz, or Hz, which stands for per second. The wavelength and the frequency are inversely related. A bigger wavelength means that fewer cycles will be completed per second and therefore has a smaller frequency. It turns out that for a wave traveling in a vacuum, the product of the wavelength, lambda, and the frequency, nu, is equal. As you can see, I've replaced the c with a nu here. So the wavelength, lambda, times the frequency, nu, is equal to c, which is the speed of light in a vacuum. C is equal to 2.998 times 10 to the 8 meters per second, which we often round up to 3.0 times 10 to the 8 meters per second. So if you ever get stuck on the relationship between frequency and wavelength, you can use this equation as a reference point. Because the wavelength and frequency are multiplied together to make a constant, when one goes up, the other must go down by a reciprocal amount to make sure they're still equal to c. Let's take a minute and explore that relationship further. If you go to this link, you'll find a little Java tutorial that demonstrates the interplay between frequency and wavelength. You'll see that there's a window with a propagating wave and 3 slider options: the frequency slider, the amplitude slider, and the wavelength slider. Do not touch the amplitude slider. Focus only on the frequency and the wavelength. Pause this video and move around the frequency and wavelength sliders and see what happens to the shape and color of the wave. Today, we're going to consider light waves that are my two favorite colors, pink, it looks pink, but it's technically violet, and blue. Start by moving the wavelength bar until the slider and waves themselves turn pink and violet, or violet. Draw what the wave looks like on your sheet and record the wavelength in nanometers and the frequency in hertz. Next, move your slider over until you hit sky or Tar Heel blue light. Draw the wave next to the pink, violet, white light that you draw on the sheet, and then record the wavelength and the frequency in the appropriate place. Take a look at your values for wavelength and frequency between the pink and or violet and the blue light. Does the wavelength increase or decrease? How about the frequency? Now take a minute and run the wavelength slider across the length of the spectrum. Although the spectrum appears to be continuous, a German physicist named Joseph von Fraunhofer noticed that the electromagnetic spectrum isn't continuous. Instead, the spectrum, specifically the visible portion, was comprised of a series of individual lines. The color of each line, called the Fraunhofer lines, correspond to a specific wavelength of light that's a specific energy from a specific particle. This becomes important when we start to talk about the energy of waves. Light waves are released as a result of a charged particle, like an electron, accelerating or colliding with another particle. This light, therefore, contains energy. It turns out that if we know the wavelength and/or frequency of a wave, we can also figure out the energy contained in that wave. Max Planck built on Fraunhofer and other observations about light, that only specific transitions or visible lines were observed, and concluded that electromagnetic radiation was quantized, or it only could be expressed in multiples of an elementary unit or quantum. Or you could only find energies with values equals to multiples of a constant named the Planck constant, conveniently after Planck. An analogy would be the stairs versus taking a ramp. Stairs are quantized, and that you can only take multiples of a single stair. 1 stair, 5 stair, 10 stairs, 300 stairs. A ramp, however, does not have an individual unit. The height change is continuous over the course of the ramp. At any given point, you're only taking a single ramp. Planck related that the energy contained in a wave was equal to Planck's constant, h, or 6.626 times 10 to the negative 34 joule seconds, multiplied by the frequency of the wave. We can also relate the energy of the wave to its wavelength. If we go back to the first equation we learned and swap in c over lambda for the frequency, the energy of the wave is equal to Planck's constant times c divided by lambda. This makes sense because we know that frequency and and wavelength are inversely related, so energy would be directly proportional to the frequency and not directly or inversely proportional to the wavelength. Pause the video and go back to your figure with the pink and blue light. Using the wavelength or the frequency as well as Planck's constant, determine the energy in joules for each wave. I'll do an example calculation here. For my pink light, which is technically violet, I chose a wavelength of 380 nanometers and a frequency of 7.89 times 10 to the 14 hertz. The energy is equal to the frequency times Planck's constant. If we multiply the two values together, the seconds and inverse seconds cancel out, and we get a value of 5.23 times 10 to the negative 19 joules. I'll make the note that if you were to calculate the energy from the wavelength and you were to have to incorporate the speed of light, you would want to account for the fact that the wavelength is in nanometers and we have the speed of light in meters. Calculate this for your own wavelength and then repeat for the blue. Look at the relationship between these two colors of light. Does the energy increase with increasing wavelength or decrease? And how is the relationship between energy and frequency? As a last exercise, here's an electromagnetic radiation spectrum below, focusing specifically on the visible domain. Use the application that you found on the internet to determine a wavelength for red, orange, yellow, and green light, along with the pink, purple, and blue light, and fill in the wavelengths on the spectrum below. Denote on this spectrum, as well as the electromagnetic radiation spectrum as a whole, the direction in which the frequency increases and the direction in which the wavelength increases. In class, we'll build on our knowledge of waves to understand how this relates to early models of the atom.